I'm the last keynote speaker, and you have been hearing a lot of sessions on different aspects of critical minerals, and I'm honored to be the last one. And I'll be talking about the environmental impacts of critical mineral supply chain. And I'm a part of Comparing Electricity Options project, as mentioned by Esti. So I know it would be awkward to start with the definition of a critical mineral, but I suppose that is needed for my presentation at least. So on the perspective of critical mineral, on the perspective of the United States, what is a critical mineral? Critical mineral is a non-fuel mineral. It is essential to the economic and national security of the United States on the perspective of US. And the supply chain is vulnerable to disruption. It serves as an essential function in the manufacturing of a product. And the last point is more important, the absence of which will have significant consequences on the economy and national security. So our studies as part of the Comparing Electricity Options at the Bureau of Economic Geology, UT Austin, was concentrated mainly on three important critical minerals on the perspective of United States. We studied cobalt, nickel, and lithium supply chains. So I'll be presenting some results based on our life cycle assessment studies, determining the environmental impacts and the cumulative energy demand of different possible supply chains. So what was the motivation of our studies? As I've already mentioned, we were looking into life cycle assessment and environmental impacts. So the first point is most important. The critical mineral supply chains should be sustainable. They should be responsible on an environmental perspective. Because if they are not, they can hinder the scaling up of storage and energy technology. Storage, of course, everybody knows the lithium-ion batteries, which are an integral part of electric vehicles, and energy technologies. Of course, solar panels, wind turbines, CCGT, all those things. And they can limit the progress on climate and energy security if we do not look into sustainable and responsible critical mineral supply chains. So what we try to do is to understand the trade-off between the society's goals of mitigating climate change, at the same time preserving biodiversity, ecosystem, and providing affordable energy, clean energy, reliable energy to the global community. So the aim of our project was to understand the local and global life cycle environmental impacts of critical mineral supply chains. So, and critical mineral supply chains as well as electricity generating technologies, and the prospects of onshoring the critical mineral supply chains on the perspective of United States. So today in the morning session, we had Professor Douglas speaking about the imports. United States is importing the magnitude of critical minerals which the United States is importing. So this is on the perspective of LCA and determining the environmental impacts if we try to onshore the critical mineral supply chains. How far is it possible, or what are the prospects? So why do we specifically select the critical mineral supply chain? Because they are the main component of batteries. Of course, we all know that in electric vehicles. And the mining and processing of critical minerals can lead to environmental impacts. And where does this environmental impacts happen? How do they happen? When do they happen? In which life cycle phase does it happen? And it can, how will this information help us to align the industry or to design the industry processes and routes with lower environmental impacts? So some of the questions which we tried to answer were, what are the life cycle environmental impacts? What is the cumulative energy demand of the different supply chain routes and for different battery chemistries, and how do they change over time? And how do they change with the geography of the supply chain route? And we have also tried to find out which is the most sustainable supply chain route among an options given using multi-criteria decision making. So we have used life cycle assessment. Many of you might be familiar with the term LCA, and this is the methodology in the form of a figure. We have different inputs, including raw materials and energy, which goes into an energy system or a process. And the process has acquiring the raw materials, manufacturing a final product, its operation, and recycling. And you get the final, the outputs in the form of the main product, which can be a battery, which can be a solar panel, which can be a wind turbine, whatever it is. and you can have byproducts also. So during this process, you can have atmospheric emissions and solid emissions or waterborne emissions, which can contribute to the environmental impacts. So the system boundary is the process which we are considering, and LCA is a standardized methodology which is ISO standard, which has ISO standards which are ruled by ISO rules, which is mentioned in the slide. And we are using OpenLCA, which is a software that is used for doing life cycle assessment, and using EcoInvent database, which is the base. Of course, we may have to customize our database based on the location we are studying, the product we are studying, and the material we are studying. So we all know, we have heard of global warming potential or water consumption or land use. These are some of the major environmental impacts which we are always concerned about. But according to the LCA methodology, we have 16 environmental impacts which we are considering or looking into. Of course, the first 3 I have already mentioned. We have acidification potential, we have ecotoxicity potential, eutrophication both on freshwater and terrestrial, and of course biodiversity and ecosystem services are also considered as part of our analysis. So that everything on the, I think in some of our previous presentations we could find carbon emissions which have been quantified for supply chains or energy or processes. But in our analysis, we try to look into all the 16 environmental impacts and look for on which perspective which is best. So it is a complete analysis on terms of, or on the perspective of environmental impacts, rather than only looking into global warming potential or water consumption. So these are the units in which they are specified. It just popped up now. So it's in terms of sulfur emissions or carbon dioxide emissions or NOx, dichlorobenzene, and land quality and habitats impacts. So this is the cradle to gate LCA boundary of minerals and metals which we use. You start from mining the metal from earth and ecosystems. It can be rare earth metals, copper, cobalt, lithium, nickel, whatever it is. It is converted to the usable form using individual processing techniques, which is the processing phase. Then you have the refining phase, and then you have the end user. So the end user or the end use phase is the power plant components or the entire power plant, as well as the storage, which I have mentioned in the slide. So this is the cradle to gate boundary of our analysis. To be more exact, we should actually look into the recycling or landfilling of the products or the end products which are produced as a result of this energy system, which is the grave phase. But the recycling and landfilling part has not been considered for our analysis because it is a whole separate, separate wing of doing LCA, where you have lot of landfilling options, lot of recycling options for batteries and other components. So life cycle assessment, why do we do it? Because we need to have an understanding of all the major environmental impacts, not only global warming potential and water consumption and land use and the geography of impacts, and to understand the environmental cost of building a system. So we can increase the boundary, or we can increase our boundary of study to include more and more processes, more and more technologies, more and more systems, and we can see how technology advancements can improve the environmental footprint of a system. So this is the LCA boundary of a battery supply chain. And here we can see that the metal ore processing, the refining, and the cobalt. And I have considered the 3 metals, cobalt, nickel, and lithium. And that is the material production phase. Then you have the manufacturing phase, where you have all the components of the battery shown, the cathode, the anode, the electrolyte, and the container. Then you have the transportation phase of the battery, and then it moves to the end user. So you have, we are doing both life cycle environmental assessment, starting from the mining or the material production to the final use phase, in which the user actually uses the battery. And we do both environmental assessment as well as life cycle cumulative energy assessment. Yeah, for cobalt, we have considered, I'll just give a crux of all the three metals which we have studied. So for the global supply chain for cobalt, we have considered 150 scenarios in total, and 3 battery chemistries, 1 mining location, which is DRC, 3 refining locations, China, Canada, and Finland. So these are some of the results. I can just quickly move through them. So one important thing which we found out was, as I have already shown, we have selected ore grades from 0.1% to 1% ore grade for the cobalt analysis. And we could find something interesting, which is the global warming potential decreases exponentially, which means when the ore grade is less, you have a very high global warming potential. The functional unit is 1 megawatt of battery. So 1 megawatt hour of battery, which means what all results I'm presenting is in terms of 1 megawatt hour of battery. So here you can see that when the ore grade is less, you have a very high global warming potential for 1 megawatt hour of battery. But as the ore grade increases, you have a steep decline in GWP. And the next figure shows the use phase. So use phase of the different battery chemistries. And here we can see that the total usage year of the battery is around 24 years. And in that case, what we have done is you can see the spikes in the use phase global warming potential. It is because as the time increases, the usage, when the battery, we keep on using the battery, its efficiency goes on decreasing and its storage capacity goes on decreasing. So in order to maintain the same storage capacity, you need to augment it with additional storage so that the storage capacity remains the same. So during the use phase, that augmentation creates additional global warming potential because we are increasing the capacity. And at the end of 22nd year, we are totally replacing the battery. So that is how it goes during the use phase of battery. Yeah, and the graph on the left-hand side shows the different battery chemistries and the refining location. Variation with the ore grade. So of course it depends upon the different battery chemistries which we have considered, that is NMC 111, 532, 622, 811, and NCA. So it of course depends upon the characteristics of the battery, the percentage of metals which are used in the battery, the mining processes, the refining processes, and all those things are evident in the graph which is shown. And the graph on the right-hand side might be a little confusing because I've shown almost all the environmental impacts in a single graph. Of course, I have mentioned it before that not all environmental impacts are of the same magnitude and they cannot be presented on the same scale because they are represented using different units. But how did I represent it in a single graph there? Because we have in eCoinvent or in OpenLCA, we have a process called single score point or single point, converting it into on the basis of a single reference. So here in this case, we can see that some of the environmental indicators have higher magnitude in comparison to of course I have presented all of them, but some of them have very higher magnitude when represented on a single reference. So this is something which I have already told, the 16 environmental impacts change with ore grade. There is an exponential decrease of GWP, operational GWP increases during augmentation and replacement, and ecotox, water consumption, and carcinogenic and non-carcinogenic toxicity are the significant environmental impacts for the cobalt supply chain. When you come to the lithium-ion battery landscape of the PRC scenario, you can see that most of the batteries are the raw materials for batteries are produced in China, and then you have some of them produced in Australia. The spodumene is mainly produced in Australia, and you have Chile, which is a common source of brine. And United States, you have the deployment of batteries. So these are some of the manufacturing facilities in the US, probably, and the materials. The raw materials are shown across some of the possibilities, some of the manufacturing locations are shown in the graph. So for the lithium supply chain, we have considered salar brine, spodumene, and 2 prospective brine routes, which is the geothermal brine and the oil field brine. This figure is similar to the one which I showed before, but this is specific to the lithium supply chain. And Just wanted to mention that we have considered four different routes for the lithium supply chain. And onto the right-hand side, you can see another block where we have done multi-criteria decision-making to identify which is the most sustainable lithium supply chain. So for the LFP battery, this was the route which we considered. We have considered the Chile-China route. We have also considered the Chile-US route. And for the geothermal brine, we have considered Salton Sea in California and oil field brine is Smackover in Arkansas. So these are prospective. Here is where I come to my initial aim of understanding what are the environmental impacts of onshoring critical mineral production in the United States. So this is the scenario for the LFP battery, and this is the scenario for the NCA battery. Here we have the same. We have considered two different prospective scenarios, geothermal brine and oil field brine. So these are some of the LCA results. I've just shown global warming potential and water consumption, comparing all the 8 supply chain routes, 4 for the LFP battery and 4 for the NCA battery. So here in this case, we can see that when we onshore it, the Chile-China route has the highest global warming potential for the LFP battery. Similarly, the China route has the highest global warming potential for the NCA battery. And when it comes to the US route, we can see there is a decrease in GWP. So we can split these numbers into 3 actually. The total GWP can be broadly divided into the contribution of material production, then the manufacturing phase, and the transportation phase. So in this case, transportation phase is minimum when we have the mineral produced in the United States and we have it used in the United States, instead of having the raw material mined somewhere, refined elsewhere, and transported to the United States for manufacturing the battery. So even though the material production contributes the highest percentage of any environmental impact, the transportation component can be less if we onshore the critical mineral supply chain. Similarly, for water consumption in general, NCA batteries have a higher water consumption in comparison with the LFP battery chain, because for the NCA we have considered hard rock mining or spodumene mining, which consumes more water. So the numbers are with reference to 1 megawatt hour of battery. So we have all the results with us, but for just demonstration purpose, I showed you global warming potential and water consumption. So this figure actually gives the percentage changes of the environmental impacts with reference to the base case. So for both the LFP battery on the left-hand side, we have the blue dots showing the Chile-China route, where the brine is in Chile and lithium is extracted, and in the China, finally the route ends at China. And all other routes are also specified in terms of colored bars, and those above 0% show that they have an increase in environmental impacts, and below the 0% shows that they have decrease in environmental impacts with reference to the base case of China. So for the LFP battery, we can see that some of the impacts are less in comparison. Most of the impacts are less in comparison to the base case. In NCA also, you have a similar case, except for ionizing radiation potential. Of course, these factors depend upon how you choose the supply chain, the parameters like electricity, grid mix, and all those things. We'll come to that factors later. So for the US upstream results, we can see that the geothermal brine, the highest, this was one of the master's thesis of our student. So this continental brine, it accounts for about 80% of the freshwater ecotoxicity impacts for the geothermal brine. And other impacts are also there, but they are comparatively less when compared to the continental brine. So the multi-criteria decision-making was used. Some of you might be familiar with MCDM. We did MCDM, of course, to select the most sustainable battery supply chain. What do you mean by most sustainable battery supply chain? You cannot select one supply chain as a best. With respect to a particular environmental impact, this chain might be the best. this route might be the best. With respect to water consumption, this route might be the best. With respect to cost, this route might be the best. So you cannot say that a specific supply chain route is the best for the production and usage of a particular critical mineral. So we have to select one based on a strategy or an option which we give among different options with different degrees of choices or preferences, which means we assign weights to different impacts and find out the most sustainable one based on that. So as we could assign weights to all the 16 environmental impacts. That was also possible. But what we did was we converted all these midpoint categories. So according to the LCA methodology, these are called the different environmental impacts which I showed are called the midpoint environmental categories or midpoint impact categories. So what we did was we mapped them to endpoint categories where they were clubbed. One or more of the midpoint categories were clubbed into different endpoint categories. That is, to be more specific, increase in respiratory diseases was contributed by some of the environmental impacts like particulate matter, ozone formation. Increase in various types of cancer had other impacts contributing to it. Of course, we all know ionization, radiation, ozone depletion, human carcinogenic toxicity. So these environmental impacts contribute in different percentages or ratios to the endpoint categories. So for reasoners, what we did was we assigned weights to the endpoint categories. We can also do the other way, but to make it more easy, we assigned weights or prioritized different endpoint categories. So the endpoint categories are also called the damage pathways. So according to recipe midpoint H, these are the endpoint categories which we identified and which we have used for our analysis. Increase in other diseases, increase in malnutrition. The first four are with respect to human health, and the next one is damage to freshwater species, which are contributed by, of course, global warming potential water consumption, freshwater ecotoxicity and freshwater eutrophication, and damage to terrestrial species, of course, contributed by terrestrial parameters, and damage to marine species, which is contributed by marine ecotoxicity. We have also considered cumulative energy demand for doing multi-criteria decision making. So these are the results, and we could see that among all the 8 supply chain routes taking all together, the geothermal brine for NCA battery has the most number of greens in it. So we can say that when we prioritize these different endpoint categories, we can say that the geothermal brine on the US route can be the most sustainable one. So this is the same thing which I just mentioned. But the last point is something which we need to take care. The LCA input parameters are very uncertain, so those will impact the results. So of course, we have to be very careful while we do when we gather the information for doing LCA. So last one is nickel supply chain. This shows the different nickel processing plants, mine sites, and refineries. So the impacts which are varied by processing technology, the different impacts varied by processing technology is shown in the slide. We can see that they vary by the technology. So environmental sensitivity to ore grade, it shows a similar pattern as I have shown before, but it of course depends upon the location, that is Indonesia to Japan, Cuba to Canada, and the process is also written there, pyrometallurgy, and the ore body also, that is, it depends upon the ore body also. So all these parameters contribute to the variation in global warming potential. Of course, all the impacts, but I've just shown GWP for representation. So as conclusion, we can say that what did we find? We found out that processing technologies, the location of the mine site, the processing plant, the transportation routes, all are deciding factors for emission. The grid mix is another deciding factor because it's dependent upon the location. When you don't have any transportation, you have the operations which can, if you are integrating all the operations in a single site, that can reduce emissions, and end product type can also impact the emissions. That is, if you use ferronickel instead of nickel metal for a stainless steel, it can be more emission intensive. So policy implications, I'm not a policy person, and probably Holiday can give more explanation and more detailing about the different policies regarding critical minerals in the United States. So I just saw this one. I could see that this was the policies which they were mentioning yesterday in the panel discussion. So the United States will be identifying new sources of critical minerals, the possible options, increasing activity at all levels. The miners and producers have electronic access, and streamlining leasing and permitting processes will increase onshoring critical mineral production. So how do our studies impact policy decision? We have to identify, explore new mine locations and sources. We should have improved processes and refining technologies, as well as transportation modes and routes. We should understand the supply chain, environmental impacts, energy demand of onshoring critical mineral production, and the best method to do that is doing life cycle assessment. If we can include recycling, that would also be fine, and that would also increase the accuracy of our results. And decision-making algorithms, as I have shown, like multi-criteria decision-making, can help us to select the most sustainable supply chain route. So in this case, I've just used the environmental factors. I can bring in economic factors. I can bring in social factors, anything to choose a sustainable supply chain route. So these are some of the publications from Comparing Electricity Options project. We have done LCE on cobalt, nickel, and lithium, and we have master's students also working on it. So my acknowledgement is to the CEO research team. Thank you very much. Any questions? I would be happy to take.